Okay. In the last lecture, we talked about R and N. And if you recall, we talked about gated R and N. And this is what actually we use in practice. And also, if you remember, I told you that it's not intuitive at all. It's not intuitively, it's not clear how and why people come up with this model with so many gates. But this is based on many experiments with this type of model and different type of scenario that you need the memory to be around, or you need to forget a part of the past, and so on. So they came up with this type of gated models, and there are many of them. The most common one is LSTM, and the oldest one. And LSTM is not one type. There are many different variations of LSTM. Told you at least 20 has been in the survey that the first author of LSTM counted up to 2015, I believe. And GRU is, a more restricted type of gated model, came after LSTM, still has many different variations. So in practice, actually, when you are making a model, you treat this LSTM or GRU as a block box that has two inputs. And one input is your observation X. The other input is the hidden unit of the previous one. And then you have HT. And if you need many layers of them, just you put them together. But inside each of them is what we explained. And you don't need, in modern packages, you don't need to be worried about the derivative and backpropagations because they take care of them automatically. Okay, we talked about vanishing gradient a lot, but we didn't talk about exploding gradient. This is another problem. So solution to exploding gradient, and the problem that actually, the problem of vanishing gradient is more severe, so there are many more solutions to handle that. The problem of exploding gradient is that, as I mentioned the other day, if you have a very nonlinear function, and search space, it's quite possible that at some points you have a huge gradient. And even if your learning step is very small, you are going to have a scenario similar to this. You are going to have something like a cliff. And your learning step is small, and you are pretty close to get to the result. But all of a sudden, you face this cliff, and has a large gradient. And it basically, if you just look at the tangent of this, it's going to shoot you to the other side of the search space. So you're going to be pretty far from the optimum when you were very close, one step away. You're going to be pretty far, and you have to search the space again and again and again. So that's typical problem of exploding gradient. Solution to this problem, the most common solution to this problem is quite hacky in terms of mathematics. You can't have a good justification for that. The most common is clipping gradient. And clipping gradient means that your gradient is 1,000, assume it's 2. So that's basically what it is. No matter what your gradient is, clip it. And so basically your gradient from now on is going to be maximum of gradient and 2, maximum of gradient and 6. So you're going to put an upper bound of your gradient. If it's larger than something, you assume that it's not. That's basically what it is. And not only in RNN, in many other cases, actually, people practice this trick, including in dropout. This hack actually has many different variations also that, clip, normalize, and then before iteration, after iteration. But anyway, I can't justify this mathematically. It's just, a hack that people use to get rid of this problem. RNN is, as we discussed before, is useful when you want to model temporal data. Your data has a sequence. For example, it's quite common in natural language processing. And the many problems with natural language processing these days are tackled through what is called sequence-to-sequence models. And sequence-to-sequence models is basically in the most basic form, sequence-to-sequence model in the most basic forms, is 2 LSTM. One LSTM is your encoder, and the other one is your decoder. So imagine one natural language processing task. Say, for example, you want to do translation from English to French. Then you're going to have encoder, and you're going to have a decoder. This is your encoder, and this is your decoder. And each of these units are LSTM. So as input of this LSTM, I have an English sentence. So this is RNN, so it can take care of this temporal sequence, this sequence. So I have a sentence. This is a book. So the first word comes to LSTM, second word, and so on. So LSTM, this is the goal. LSTM eventually makes a fixed length vector for any sentence, no matter what the length of the sentence is. So it's a sentence with 3 words or a sentence with 100 words. You can map it to a fixed length vector at the end of this LSTM as the output. Okay? So make this input to the decoder. But the decoder is supposed to make a sequence. Okay? So again, you have back-to-back model, which is common in neural network. You give input, you take the output. So your input is English sentence, your output is a French sentence. What's happening at the middle is that the English sentence will be translated to a fixed length vector, and this fixed length vector will be translated to a new set of characters, which happen to be French because you train it on French. Okay? Many other models, like correction. You have grammatical error in a sentence and you want to make correction. There are data sets that you have sentence with grammatical error and you have the correct sentence. And in this correction, actually, there are a couple of operators. Deletion, basically when they want to correct, you have to delete this word and you have to insert this word. So a couple of finite number of operators will be applied to this sentence, to each word of this sentence, and give you a new sentence. Delete this word, add this word, and so on. And then again, it's back to back by sequence-to-sequence model. You train it. And translation, grammatical correction, text generation, you have a sequence of words as the input of your LSTM, and you want to predict the next word. And then you add this next word to the sequence. Now that's your sequence. And then you're going to predict the word after. So by nature, most of this natural language processing models have the same or similar structure and similar, actually, concept are behind it. Yes?
The fixed length word, fixed length vector, which you apply between the nouns. So if I have like a 10-word sentence in English, and if I have 3 length vector, how can it generate the words in French based on a fixed length vector? Because is it compressing or what is it doing exactly?
No, it's not compressing. That's the way that you train it, this sentence basically, it's first of all, it's the most simplest model, introduced in this paper, what I explained. There are things that has been added to this, like attention model, that if we have time, we'll talk about it later on in the course. But it's basically how you train your model, You decide that each sentence is going to be mapped in this vector space. Each sentence is going to be mapped to this d-dimensional vector, right? What's important is that the concept should be, the meaning basically should be carry over to the new sentence. You can think of this as you think about a concept and then you express the concept, right? If you know two different languages, your thought is the same, and then you decide to express it in English or you decide to express it in French, right? But what you have in mind is a hidden space which can be mapped to both of these two different languages. That's the same, as if we are capturing or we are computing that hidden space which you have in your mind, How can I turn it back to this hidden space that I had in mind and then now turn it? Anything that you have in mind will be mapped to French through this decoder. Anything that is in English will be mapped to what you have in mind through this encoder.
So the input length doesn't really matter?
It doesn't matter, no. In different languages, you may be able to express a 10-word sentence in 3 words, It's not a restriction that I have to have the same similar. But as usual, there are many, many tricks involved here to get them to work. What I'm explaining to you is the base concept. There are attention models. Before attention models, people used to train a sentence in encoder and make it backward in decoder. The order of the words is backward in decoder because, when you get to the last word, you're going to forget what was the first word. If you change the order, it's going to help. And then there's attention model that if you have time, we're going to explain it, would fix this. There are many sort of heuristic and hacks and tricks to make them work, but this is the base. The base is that map everything to the space of concepts, and from concepts get back, materialize this concept in a different language.
Should there be an upper bound on the
length?
Yeah, because certain concepts can be conveyed in a very large fashion because it's actually complicated.
Mm-hmm.
Certain concepts are very easy, so how will you put an upper bound on the concept?
In practice, there will be an upper bound because you're training with a training set that maximum length of a sentence is some. And if you train it with, very, very long sentence, I'm sure without attention model or without this type of tricks, it's not going to work because when you get to the end, you forget what was the first part of the sentence. Okay. So this is basically sequence-to-sequence model that you're going to use in natural language processing in chatbots, for example. Chatbot is almost the same. You have the input and you have the answer of the input. Question answering, you have question, you have the answer. The base of all of them are pretty similar to each other. Yes?
I've heard that a strength of these models is that they can handle input and output of varying length.
Mm-hmm.
But for the output at least, how do you practically do that? Do you have an output vector of arbitrarily long length, and then after your translation is done, output null characters or something?
No. You think of this as conditional probability. Say your English sequence is X and your French sequence is Y. And think of this as like Y1, Y2, Y3, and X1, X2, X3. And now think that you want to maximize the probability of y given x. So at each step, you shouldn't, in practice, shouldn't wait until the sentence is complete and then start to translate it. Suppose that I have one additional word, and what should I add to y to make the probability of y, the posterior, the probability of conditional probability, y given x maximum. Among all possible words in French, what word should I? And it's not just word, it could be, a period, or it could be question mark. These are also one of, in the set of your characters, possibilities. So naturally, a sentence will end somewhere, and another word comes after, But don't think of this in practice that, a complete sentence should be fit and then a complete sentence. In practice, you can look at it as a sequence.